Hello students, today's lesson is on linear homogeneous differential equations with constant coefficients. This is for PG mathematics students in the course of differential equations. In this lesson, you are going to learn about what is an initial value problem and boundary value problem, what is the linear independence and dependence, and similarly what is the definition of the Wronskian of set of two functions or n functions, and what is the connection between linear independence and Wronskian of set of two functions, and finally finding all possible solutions of the linear homogeneous differential equation with constant coefficients. The general form of nth order linear homogeneous differential equation with constant coefficients is y to the power n plus a1 y power n minus 1 plus and so on plus an into y is equal to 0, where a1, a2 and so on an are all constants. The general meaning of the solution is nothing but, suppose there is a real or complex valued function phi of x defined on an interval I of the real line is a solution of the equation nth order equation if the derivatives of phi of x are all exist and phi of x satisfies that nth order equation, like pi to the power n of x plus a1 pi to the power n minus 1 of x plus and so on plus an pi of x is equal to 0 for all x belongs to I. The main aim of this lesson is finding all possible solutions of the given differential equation, but sometimes we have to find a unique solution of the given differential equation. It is possible by all solutions which satisfy some type of conditions. There are very important conditions like initial condition and boundary condition. Now first of all, I will give what is an initial condition. An initial condition is a condition on the solution of the differential equation at a single point. And the problem of finding all possible solutions of a given differential equation which satisfy a given initial condition is called an initial value problem. The first order initial value problem will be like this: y dash plus ay is equal to 0 is the differential equation and the given initial condition is y of x naught is equal to alpha. Here x naught is a known value or initial point and alpha is a given constant value. And similarly, the second order initial value problem is y double dash plus a1 y dash plus a2 y is equal to 0 is a differential equation and the given initial conditions are y of x naught is equal to alpha, y dash of x naught is equal to beta. Here alpha, beta are given constant values and x naught is initial point as well as known value. Similarly, the nth order initial value problem is y power n plus a1 into y power n minus 1 plus and so on plus an into y is equal to 0 is a differential equation. Here the given n initial conditions are y of x naught is equal to alpha 1, y dash of x naught is equal to alpha 2 and so on y power n minus 1 of x naught is equal to alpha n. Here alpha 1, alpha 2 and so on alpha n are given constants. X naught is a single point as well as initial point. For first order initial value problem, it has only one initial condition. For nth order initial value problem, it has n initial conditions. So from this we can say the number of initial conditions depends on the initial value problem of the order. Now I will give example here. Find all solutions of the differential equation y dash minus y is equal to 0 on minus infinity comma infinity. The given equation can be written as d minus 1 into y is equal to 0. Here capital D is differential operator and dy by dx is denoted by capital D of y. As you know that the auxiliary equation is m minus 1 is equal to 0. So you know that this is algebraic equation of degree 1, so that it has one root, that is m is equal to 1. Now I will write the general solution of this equation, that is y is equal to c into e power x. Here c is an arbitrary constant and the root 1 can be written as the coefficient of x in the exponential form. So if you observe here, there are infinitely many solutions because c is an arbitrary constant in the general solution. So that we can eliminate that c by using given initial condition from the given problem. For that I will give another example here. Solve an initial value problem y dash plus y is equal to 0 is a differential equation, y of 3 is equal to 1 is an initial condition. As I explained previous example, the given equation can be written as d plus 1 into y is equal to 0. Here the auxiliary equation is m plus 1 is equal to 0. M is equal to minus 1. Minus 1 is the root of the algebraic equation. So now I will give the general solution of this given differential equation, y is equal to c e power minus x. Here c is an arbitrary constant. So we can say there are infinitely many solutions here. But we can eliminate this c by using given initial condition, that is y of 3 is equal to 1. For that, put x equal to 3 in the general solution. Then we have c e power minus 3 is equal to 1. Therefore, c is equal to e power 3. Put the value of c in the general solution. Then we have y is equal to e power 3 into e power minus x. This is equal to e power 3 minus x for all x belongs to minus infinity comma infinity. So is there any arbitrary constant in this solution? No, there is no arbitrary constant, so that it is a unique solution of the given initial value problem. Now I will give what is the boundary condition and what is the boundary value problem. For that, a boundary condition is a condition on the solution of the differential equation at 2 or more points. And the problem of finding all possible solutions of a given differential equation which satisfies the given boundary conditions is called a boundary value problem. For example, the boundary value problem of second order is known as y double dash plus a1 y dash plus a2 y is equal to 0 is the differential equation, and the given boundary conditions are y of x0 is equal to alpha, y of x1 is equal to beta. Observe here x0, x1, there are 2 points here. These are endpoints of the interval x0 comma x1, and as you know that alpha and beta are given constant values. Now I will give one more example based on boundary value problem. Solve the boundary value problem for all x belongs to R. Y double dash plus y is equal to 0 is the differential equation, and the given boundary conditions are y of 0 is equal to 0, y of pi is equal to 0. Now we are going to solve this boundary value problem. The given equation can be written as d square plus 1 into y is equal to 0. You know that what is the auxiliary equation here? M square plus 1 is equal to 0. And this is the algebraic equation of degree 2. So that it has 2 roots. M square is equal to minus 1 and m is equal to plus or minus I. This root of the equation is like alpha plus or minus I beta. For this, the solution is e power alpha x into c1 cos beta x plus c2 sin beta x. According to this, our solution can be written as y is equal to c1 cos x plus c2 sin x. Observe here, there are two arbitrary constants C1 and C2 in this solution because it is the second order equation. But we want to eliminate these two arbitrary constants by using given two boundary conditions. Y of 0 is equal to 0, y of pi is equal to 0. From the first boundary condition, put x equal to 0 in the general solution. Then we get C1 is equal to 0. From the second boundary condition, put x is equal to pi in the general solution. Then we get C1 is equal to 0. And put the value of C1 in the general solution to overcome the arbitrary constant C1. Y is equal to C into sin x. This is the solution of the boundary value problem. If you compare both initial value problem and boundary value problem, here if you solve boundary value problem, even though we can say from this example, this boundary value problem can have infinitely many solutions or one solution or none solutions. Now I will come to what is the linear dependence and linear independence of two functions here. This is the necessary concept of finding all possible solutions of the given differential equation. Two functions pi1, pi2 are said to be linearly dependent on I if there exist two constants C1 and C2 such that C1 pi1 plus C2 pi2 is equal to 0, which implies that both C1 and C2 should not be 0 here. That two functions pi1 and pi2 are said to be linearly independent if they are not linearly dependent. That is, if the constants C1 and C2 such that C1 pi1 plus C2 pi2 is equal to 0 for all x belongs to I, which implies that both C1 and C2 should be 0. Now I will give example based on linear dependence and linear independence. The functions x, mod x are linearly dependent on the interval 0, infinity and linearly dependent for all x belongs to R. Suppose we know that C1 pi1 plus C2 pi2 is equal to 0. Here pi1 is x, pi2 is modulus x. Then we have C1x plus C2 modulus x is equal to 0. As you know that modulus x becomes positive values of x when x greater than 0. Modulus x becomes negative values of x when x less than 0. That is, when x is defined on the interval R, that means for all x belongs to R, then that equation becomes C1x plus C2 mod x is equal to C1x plus C2x is equal to 0 when x greater than 0. For x less than 0, C1x plus C2 modulus x is equal to C1x minus C2x is equal to 0. We know that x is not equal to 0, so that from the both equations C1 plus C2 is equal to 0, C1 minus C2 is equal to 0. Now we have to solve both equations. After that we get C1 and C2 both zeros. Then we can say the given functions are linearly independent. When x defined on the interval 0, infinity, in this interval the values of x are positive values. For that, C1x plus modulus of x into C2 is equal to C1x plus C2x is equal to 0. Since x is not equal to 0, so that C1 plus C2 is equal to 0. For that, we have C1 is equal to 1, C2 is equal to minus 1. From this one we can say both are not equal to 0, so that the given functions are linearly dependent when x is defined on the interval 0, infinity. Now I will give another definition of the Wronskian of two functions. Pi1, pi2 are two differentiable functions defined on a real interval I. Then the determinant pi 1, pi 2, pi 1 dash, pi 2 dash, which is equal to pi 1, pi 2 dash minus pi 2, pi 1 dash for all x belongs to I, is called the Wronskian of pi 1 and pi 2. It is denoted by capital W of pi 1 comma pi 2 of x. Now I will give very important theorem in this lesson. Let pi 1, pi 2 be two differentiable functions on I, and the Wronskian of pi 1, pi 2 at x naught is not equal to 0 for some x naught belongs to I. Then pi 1, pi 2 are linearly independent on I. Now I will come to proof of this theorem. Suppose C1, C2 are constants such that C1 pi 1 plus C2 pi 2 is equal to 0 for all x belongs to I. Now we write this equation in matrix form, that is 2 by 2 matrix into 2 by 1 matrix is equal to 2 by 1 matrix. For example, pi 1, pi 2, pi 1 dash, pi 2 dash, C1, C2 is equal to 0, 0. Here the coefficient matrix is pi 1 of x naught, pi 2 of x naught, pi 1 dash of x naught, pi 2 dash of x naught. The determinant of this coefficient matrix is pi 1, pi 2 dash minus pi 2, pi 1 dash at x naught. As you know that this is the Wronskian of pi 1, pi 2 at x naught from the definition of the Wronskian. From the hypothesis, Wronskian of pi 1, pi 2 at x naught is not equal to 0, so that we have C1, C2 is equal to 0. That means both C1 and C2 are zeros. If both zeros, from the definition, the given functions pi 1, pi 2 are linearly independent. But the converse need not be true. That is, if the given functions are linearly independent, then Wronskian of pi 1, pi 2 at x naught may be 0 or may not be 0. For clear information, I will give example for this. We proved that x and modulus x are linearly independent for all x belongs to R. We have seen this. But Wronskian of x modulus x is equal to determinant of x, x, 1, 1 when x greater than 0 and determinant of x minus x, 1, minus 1 when x less than 0. The value of first determinant is x minus x is equal to 0 if x greater than 0. The value of second determinant is x minus x is equal to 0 when x less than 0. Therefore, we can say Wronskian of both functions x modulus x is 0. What did you understand from this? If the given two functions are linearly independent, Wronskian of that two functions may be 0, may not be 0. But Wronskian of two functions is not equal to 0, then definitely that two functions are linearly independent for all x belongs to R. Now I will give one theorem here. This is known as Wronskian formula. Let pi 1, pi 2 be two solutions of L of y is equal to 0 on I and x naught belongs to I. Then Wronskian of pi 1, pi 2 of x is equal to e power minus a1 x minus x naught into Wronskian of pi 1, pi 2 at x naught. Now I will come to proof of this result. Suppose pi 1, pi 2 are two solutions of second order equation y double dash plus a1 y dash plus a2 y is equal to 0. If pi 1, pi 2 are two solutions of the second order equation, then it satisfies that equation. That is, pi 1 double dash plus a1 pi 1 dash plus a2 pi 1 is equal to 0 and pi 2 double dash plus a1 pi 2 dash plus a2 pi 2 is equal to 0. the first equation is multiplied by minus pi 2 and the second equation is multiplied by pi 1. After getting this, we have to add both equations. Then we have pi 1 pi 2 double dash minus pi 2 pi 1 double dash plus a1 pi 1 pi 2 dash minus pi 2 pi 1 dash is equal to 0. We know that pi 1 pi 2 dash minus pi 2 pi 1 dash is nothing but Wronskian of pi 1 and pi 2. It is denoted by capital W. And what is the derivative of that capital W? Pi 1 pi 2 double dash minus pi 2 pi 1 double dash. So that this equation can be written as W dash plus A1 into W is equal to 0. You know that this is the first order linear homogeneous differential equation with constant coefficients. So that the general solution of this equation is W is equal to C e power minus A1 into x, where C is an arbitrary constant. We can eliminate this C by using x naught belongs to I. This is given point from the hypothesis. Put x is equal to x naught in the general solution. Then we have W of x naught is equal to C into e power minus A1 x naught, which implies that C is equal to e power A1 x naught into W of x naught, here plus A1. Put this value of C in the general solution to avoid C to get unique solution. That is, W of x is equal to e power minus A1 into x minus x naught into W of x naught. This is known as Wronskian formula for two functions. You know that this result can also be extended for n functions also. Now I will give example here. Find all solutions of y double dash minus 6y dash plus 9y is equal to 0. As I explained you, the given equation can be written as d square minus 6d plus 9 into y is equal to 0. What is the auxiliary equation for this differential equation? M square minus 6m plus 9 is equal to 0. The roots of this equation is 3, 3. These are repeated roots. Therefore, we have two linearly independent solutions like e power 3x, x into e power 3x. By using these two linearly independent solutions, we can write the general solution like y is equal to c1 e power 3x plus c2 x into e power 3x. So, in this lesson, you have studied how to solve the initial value problem and how to find all possible solutions of the linear homogeneous differential equation with constant coefficients. Thank you.